Welcome to this coding walkthrough. In this session, we'll dive into LeetCode problem number 1223, Dice Roll Simulation. This problem challenges us to determine the number of valid dice roll sequences given specific constraints. It's an excellent opportunity to sharpen your dynamic programming skills. Let's get started. In this problem, we are working with a dice that has 6 faces, numbered from 1 to 6. The dice will be rolled n times, and the results of these rolls will form a sequence. However, there are specific restrictions in place. These restrictions are defined by an array called rollmax, which has 6 elements. Each element in rollmax specifies the maximum number of consecutive times a particular face of the dice can appear in the sequence. For example, if rollmax 0 is 2, then the face numbered 1 can appear at most twice in a row. The goal is to calculate how many distinct sequences can be generated while satisfying these constraints. Since the total number of sequences could be very large, the result must be returned modulo 10 to the power of 9 plus 7. We are given 2 inputs, n, the number of rolls, which can range from 1 to 5,000, and rollmax, an array of 6 integers where each value is between 1 and 15. The output is an integer representing the count of valid sequences that adhere to these restrictions. Let's take a look at an example to clarify the problem. Suppose n is 2, meaning we roll the dice 2 times, and the rollmax array is 1, 1, 2, 2, 2, 3. This means that faces 1 and 2 can appear at most once consecutively, while faces 3, 4, and 5 can appear at most twice consecutively, and face 6 can appear at most 3 times consecutively. With these constraints, there are exactly 34 valid sequences that can be formed. For example, 1, 2, 2, 3, and 6, 6 are all valid sequences because they respect the rules defined by rollmax. However, a sequence like 1, 1 would not be valid because face 1 appears more than once consecutively, which violates the constraints. Now consider another example where n is 3, meaning we roll the dice 3 times, and the rollmax array is 1, 1, 1, 1, 1, 1. Here, each face can appear at most once consecutively, which imposes very strict constraints on the sequences. Under these conditions, there are 30 valid sequences. For instance, sequences like 1, 2, 3, 6, 5, 4, and 1, 3, 2 are all valid because no face appears consecutively. Any sequence where a face repeats, such as 2, 2, 3, would not be valid. This highlights how the stricter constraints from rollmax can significantly reduce the number of valid sequences. Let's take another example to explore further. In this example, n is 4, so the dice is rolled 4 times, and the rollmax array is 2, 1, 1, 3, 3, 2. According to these constraints, face 1 can appear at most twice consecutively, face 2 can appear at most once consecutively, face 3 can also appear at most once consecutively, and faces 4 and 5 can each appear at most 3 times consecutively. Finally, face 6 can appear at most twice consecutively. With these rules, there are 108 valid sequences that can be formed. This example demonstrates how varying the values in rollmax can create more or fewer restrictions, directly impacting the total number of valid sequences. When solving this problem, it's important to consider several edge cases. For instance, if n is 1, the smallest possible value, the result will always be 6 because each face can appear exactly once, and there are no consecutive rolls to restrict. On the other hand, if rollmax contains very large values, such as 15, 15, 15, 15, 15, 15, the constraints become ineffective because they won't limit the sequence significantly, and the result will depend mostly on n. In contrast, when rollmax contains very small values, such as 1, 1, 1, 1, 1, 1, the restrictions are very strict, and many sequences will be invalid. Finally, for large inputs such as n equals 5,000, the problem requires an efficient dynamic programming approach to handle the computation within reasonable time and space limits. These edge cases highlight the importance of carefully designing the algorithm to work across different scenarios. To solve the dice roll simulation problem, we need to determine how many valid sequences of dice rolls can be created while adhering to specific constraints on consecutive rolls. The primary challenge is handling these constraints efficiently, especially as the sequence length increases. One approach we considered is the brute force method. Here, we generate all possible sequences of dice rolls of length n and check each sequence against the given constraints. While straightforward, this method has a time complexity of 6 to the power of n, as there are 6 possible outcomes for each of the n rolls. This exponential growth makes it impractical for large values of n, such as 10,000. Next, we explored a recursive approach with memoization. Instead of generating all sequences, we use recursion to calculate the number of valid sequences while storing intermediate results to avoid redundant calculations. We define a state dp, I, previous, count, that represents the number of valid ways to complete the sequence starting at roll I, given the previous roll was previous and it has been rolled count times consecutively. While this approach reduces redundant work compared to brute force, the state space scaling with n, the 6 dice faces, and the maximum roll limit can still be quite large. Additionally, the overhead of recursive calls makes it less efficient for very large constraints. Finally, we arrive at the dynamic programming approach, which builds on these ideas to optimize both time and space complexity. By leveraging key observations and structuring the problem appropriately, this method provides a scalable and efficient solution. The dynamic programming approach relies on breaking the problem into smaller subproblems. The number of valid sequences at any point depends only on 3 factors: the current roll index, the last die face rolled, and how many times that face has been rolled consecutively. Using this insight, we define a DP table where DP, I, J, K, represents the number of valid sequences of length I with the last roll being J, rolled consecutively K times. To compute the transitions, for each possible current roll J, we consider all valid previous rolls and update the DP table accordingly. The base case initializes sequences of length 1, where each die face is valid. The final result is obtained by summing all valid states at the last roll index. This approach ensures that the constraints are respected throughout the computation. The complexity of this solution is n*6* max_roll_limit, where max_roll_limit is the highest constraint on consecutive rolls. Despite this, it remains computationally efficient within the problem's constraints. The dynamic programming approach was chosen because it avoids the exponential growth of brute force and eliminates the overhead of recursive calls, making it both time and space efficient. The chosen strategy for solving the dice roll simulation problem is the dynamic programming approach. This method stands out due to its efficiency and structured design. By breaking the problem into smaller subproblems, it systematically computes the solution while avoiding redundant calculations. This makes it scalable for large values of n, unlike the brute force method, which becomes infeasible due to exponential growth. Compared to the recursive approach with memoization, dynamic programming eliminates the overhead associated with recursive calls and provides a more straightforward way to iterate through states. Additionally, the DP state and transitions are carefully designed to respect all constraints while minimizing computational overhead. When comparing the trade-offs, brute force, while simple, is highly inefficient for large inputs. The recursive method improves on this but is still limited by the size of the state space and the cost of recursion. In contrast, dynamic programming strikes the right balance between time and space complexity, making it the optimal choice. Ultimately, this approach provides the best trade-off between efficiency and implementation complexity, ensuring a robust and scalable solution to the problem. The dice roll simulation problem challenges us to determine the total number of valid dice roll sequences of a given length, n, under specific constraints. Each dice roll can result in numbers from 1 to 6, but for each possible number, the maximum number of consecutive rolls is limited by the rollmax array. For example, if rollmax 0 is 2, the number 1 cannot appear more than 2 times in a row. Since the result can grow large, we must return it modulo 10 to the power of 9 plus 7. To solve this, we approach the problem using dynamic programming, which is well suited for problems involving combinatorics and constraints. By breaking down the problem into smaller subproblems, we can efficiently calculate the total number of valid sequences while adhering to the given rules. To implement our solution, we define a 3D dynamic programming table, DP, I, J, K. Here, I represents the sequence length, J is the face value of the last dice roll, and K is the count of consecutive rolls of J. The value of DP, I, J, K, represents the number of valid sequences of length I where the last roll is J and it has been rolled K consecutive times. We start with the base case. For sequences of length 1, there's exactly one valid sequence for each face value, so dp1 j1 equals 1 for all j from 1 to 6. The transition relation then helps us build longer sequences. If the current roll is the same as the previous roll, meaning k is greater than 1, we extend the sequence by setting dp I j k equal to dp I1 j k1. If the current roll is different, that is, k equals 1, we calculate dp I j 1 by summing all valid sequences from the previous step where the last roll was not j. This summation step adds new sequences where the last roll is different from the current roll. To optimize this process, we avoid recalculating sums repeatedly. Instead, we maintain a running total of valid sequences for each face value at the previous step using a prevsum array. This optimization significantly reduces redundant calculations. Once we've updated dp for all sequence lengths, we calculate the final result by summing all valid sequences of length n. Specifically, we sum dp n j k for all j from 1 to 6 and all k from 1 to rollmax j1. Finally, we return this result modulo 10 to the power of 9 plus 7 to ensure the output remains manageable. This approach balances the need for accuracy with computational efficiency. Key insights for this algorithm include minimizing redundancy and effectively handling constraints. By using the prevsum array, we avoid repeatedly iterating through all possible counts for each face value, which improves performance. Modulo arithmetic is applied at every step to prevent overflow and keep values within a manageable range. Additionally, edge cases like n equals 1, very large n, or rollmax values that are uniformly small, such as all being 1, must be carefully handled to ensure correctness. The primary data structure here is the 3D DP table, which stores intermediate results to avoid recomputation. Its size is proportional to n times 6 times the largest value in rollmax. The overall time and space complexity of the algorithm are both O and *6 max roll, where max roll is the maximum allowed consecutive rolls for any face value. To illustrate how the algorithm works, let's consider an example where n equals 3 and rollmax is 1, 1, 2, 2, 2, 3. First, we initialize the base case with dp 1 j 1 set to 1 for all j from 1 to 6. Next, for sequences of length 2, we compute dp 2 j k for all valid j and k, using the transition relations and updating the prevsum array for optimization. We then repeat this process for sequences of length 3, computing dp 3 j k based on the rules we've defined. Finally, we sum up all valid sequences of length 3 across all face values and return the result modulo 10 to the power of 9 plus 7. This systematic approach ensures the constraints are respected while maintaining computational efficiency. This code solves the dice roll simulation problem using dynamic programming. The dp table is defined with dimensions n plus 1 and thick 7, where dp I j represents the number of valid sequences of length I that end with the face j, or 6 for any face. The base case initializes dp 0, 6 to 1 as there is one way to have an empty sequence. For each roll from 1 to n, and for each face of the dice, 0 to 5, the solution calculates the count of valid sequences by iterating through possible previous rolls constrained by rollmax. It ensures that consecutive constraints are respected by subtracting invalid sequences where the current face exceeded its allowed consecutive rolls. Finally, dp roll 6 is updated to store the total count of valid sequences of the current length by summing over all faces. The result is returned as dp n 6, representing the total number of valid sequences of length n modulo 10⁻9 plus 7. Here, we start by defining our solution class in Java and importing the necessary utilities. At the top, we declare a constant mod, which is set to 1,000,000,007. This will help us handle large numbers and ensure we work within the constraints of modular arithmetic. Next, we define the method dicesimulator, which takes two inputs, n, the number of dice rolls, and rollmax, an array specifying the maximum consecutive rolls allowed for each face of the die. Within this method, we initialize a 2D array dp, where dp roll face stores the number of valid ways to roll the dice such that the last roll ends with the given face. Additionally, dp roll 6 will be used to store the total number of ways to roll dice. We set dp 0, 6 to 1 as our base case, representing one way to roll 0 dice. Now, we iterate through each roll from 1 to n. For each roll, we loop through all 6 faces of the die. Using rollmax, we determine the limit for consecutive rolls of the current face. Then, for every possible number of consecutive rolls previous, we calculate the number of ways to reach the current state while respecting the constraints. This involves taking the total from dp rolled previous 6, subtracting the invalid cases for the current face, and applying the modulus operation to ensure we stay within bounds. Finally, we update dp roll face with the computed value, again applying modulus to avoid overflow. After processing all faces for the current roll, we calculate the total number of ways to roll dice by summing up the values in dp roll face for all 6 faces. This sum is stored in dp roll 6, and we ensure it remains within the modulus by applying the mod operation. Once the loops are complete, the method returns dp n 6, which represents the total number of valid sequences of n dice rolls that satisfy the given constraints. This approach efficiently uses dynamic programming to solve the problem within the constraints, leveraging modular arithmetic and careful state tracking to handle the complexity of the dice rolls. In this problem, we're tasked with finding the total number of valid dice roll sequences of length n, where each dice face has a limit on how many times it can appear consecutively, as defined by the rollmax array. The result needs to be returned modulo 10 to the power of 9 plus 7 to handle large numbers. To solve this, we utilize dynamic programming. The key idea is to define a state dp I, j, which represents the number of valid sequences of length I that end with the dice face j. Additionally, we maintain dp I, 6, to store the total number of valid sequences of length I across all dice faces. This allows us to efficiently calculate results for each sequence length while adhering to the given constraints. Let's consider an example with n equals 2 and rollmax equals 1, 1, 2, 2, 2, 2. Here, dp is a table of size, n plus 1, x7, initialized to 0. Initially, dp 0, 6 is set to 1 because there's exactly one valid sequence of length 0, which is the empty sequence. Now, for the first roll, we calculate dp 1 face for each dice face from 0 to 5. For faces 0 and 1, the rollmax value is 1, so each face can appear only once, meaning the number of valid sequences ending with those faces comes from the total sequences of length 0. For face 0, we calculate dp 1, 0 as dp 0, 6, dp 0, 0, which gives us 1. Similarly, we calculate values for the other faces, and since all faces can appear at least once, dp 1, 6, the total number of valid sequences of length 1 is the sum of dp 1, 0 through dp 1, 5, resulting in 6. In the second iteration, where roll equals 2, we calculate dp 2 face for each dice face. For instance, for face 0, since its rollmax is 1, any sequence ending with face 0 must transition from sequences that do not end with face 0. Thus, dp 2, 0 is calculated as dp 1, 6, dp 1, 0, which equals 6 minus 1, giving us 5. We repeat similar calculations for the other faces, accounting for their respective rollmax constraints. Once all values are computed for this roll, we find dp 2, 6, the total number of valid sequences of length 2, by summing up dp 2, 0 through dp 2, 5. This results in a total of 50 valid sequences. Now, let's examine a more complex example where n equals 3 and rollmax equals 1, 1, 1, 2, 2, 3. As before, we initialize dp 0, 6 to 1 for the empty sequence. For the first roll, we compute dp 1 face, similarly to the previous example, resulting in dp 1, 6 equals 6. In the second roll, we calculate dp 2 face and find dp 2, 6 equals 50. For the third roll, consider face 0, where rollmax is 1. Sequences ending with face 0 must transition from sequences that do not end with face 0, so dp 3, 0 is calculated as dp 2, 6, dp 2, 0, which equals 50 minus 5, giving us 45. We then repeat the calculations for all other faces, adhering to their individual rollmax constraints. After computing the values for all dice faces, we sum up dp 3, 0 through dp 3, 5 to obtain dp 3, 6, the total number of valid sequences of length 3. This results in dp 3, 6 equals 450. In conclusion, this algorithm leverages dynamic programming to efficiently calculate the number of valid sequences for varying lengths, while respecting the constraints defined by rollmax. Modular arithmetic ensures the result remains within bounds, and the use of DP allows us to systematically track the transitions and totals at each step, solving the problem for any valid input size. To understand the time complexity of our solution, we start by analyzing the loops in the algorithm. First, the outermost loop runs n times, corresponding to the number of dice rolls. Inside this, we have a second loop that iterates 6 times, once for each face of the die. Then, for each face, there's an inner loop that iterates up to rollmax face times, where rollmax face is the maximum number of consecutive rolls allowed for that face. In the worst case, this upper limit, denoted as k, is constant across all faces. Within the innermost loop, the operations like accessing elements in the DP table and performing modular arithmetic are O(1). Combining these factors, the time complexity can be expressed as O(n) for the outer loop, O(1) for the face loop since it's constant, and O(k) for the inner loop. Multiplying these together gives us an overall time complexity of O(n*k). Now, let's consider the space complexity of our solution. The dominant factor here is the DP table, which is a 2D array with dimensions n+1 x 7. The first dimension represents the number of rolls, ranging from 0 to n, which makes it n+1. The second dimension represents the 6 faces of the die, along with an extra column for DP, roll, 6, resulting in a size of 7. This means the total memory used by the DP table is n+1*7, which simplifies to O(n). Apart from the DP table, the algorithm uses a few additional variables like limit and previous, but these require constant space, or O(1). Therefore, the total space complexity of the solution is O(n). When we compare this dynamic programming solution to a brute force approach, the difference in efficiency becomes clear. A naive solution would involve generating all possible sequences of dice rolls, which amounts to 6*n sequences, and then validating each sequence against the rollmax constraints. Since checking each sequence takes O(n), the total time complexity for the brute force method would be O(6 to the power of n*n), which is exponential and highly inefficient. In contrast, the dynamic programming solution reduces this to O(n*k) by breaking the problem into smaller subproblems and reusing the results of previous computations. This efficiency is supported by analyzing the iterations. The algorithm processes all rolls n, all 6 faces of the die, and the maximum limit per face k, with O(1) operations inside the loops. This justifies the derived time complexity of O(n*k) and space complexity of O(n). To evaluate the algorithm further, we can examine the best, average, and worst case scenarios. In all cases, the time complexity remains O(n*k), because the structure of the nested loops does not change based on the input. The outer loop always iterates n times, and the inner loops iterate according to the fixed constraints of the problem. This consistency means the best, average, and worst case complexities are all the same. In summary, the time complexity of the solution is O(n*k), where n is the number of rolls and k is the maximum constraint from rollmax. The space complexity is O(n), driven by the size of the DP table. Overall, this dynamic programming approach is significantly more efficient than the brute force method, reducing exponential complexity to a manageable polynomial time. When working on this problem, there are a few common mistakes to watch out for. First, one of the most frequent errors is ignoring the constraint on consecutive numbers. If you fail to account for the maximum number of times a dice face can appear consecutively, you'll end up overcounting invalid sequences. This is why it's critical to integrate this constraint directly into your state transitions. Another issue arises when defining your dynamic programming state incorrectly. For example, if your state doesn't include the count of consecutive rolls, it becomes impossible to enforce the constraints properly, leading to ambiguous or incomplete transitions. Efficiency is another key area. If you don't optimize your state transitions, the time complexity can grow quickly. For instance, iterating over all possible sequences instead of leveraging memoization or pre-computing results can cause your solution to become infeasible for larger inputs. Additionally, forgetting proper modulo handling can result in overflow errors or incorrect answers when the result must be returned modulo 10 to the power of 9 plus 7. Finally, overcomplicating the base case is a subtle but frequent issue. Always start with simple examples, such as sequences of length 1, to validate your initialization logic. This ensures your foundation is solid before moving on to larger cases. Now, let's focus on some insights that can help you during interviews. Identifying patterns is crucial. Problems with constraints on consecutive elements often rely on multi-dimensional dynamic programming. The faster you recognize this, the better. Another important aspect is state optimization. Think about how you can reduce the state space to improve efficiency. For instance, rolling sums or other techniques may allow you to handle constraints without explicitly storing every possible state. Testing edge cases is also essential. Be sure to verify your solution with the smallest and largest values of n, as well as scenarios with the tightest constraints, like when the maximum roll length is just 1. You should also be comfortable with modular arithmetic, as it's a common requirement in dynamic programming problems involving large numbers. Lastly, if you're stuck, try relating the problem to similar dynamic programming challenges. For example, problems like coin change or tiling share structural similarities and can offer inspiration for solving this one. This problem also connects to several related problems that can help build your understanding. For example, LeetCode 70, climbing stairs, is a classic dynamic programming problem that's great for practicing basic state transitions. Another useful problem is LeetCode 931, minimum falling path sum, which involves constraints on transitions, making it similar in structure. LeetCode 357, count numbers with unique digits, is another example, as it requires careful counting under specific constraints, much like this problem. Finally, LeetCode 198, house robber, is a simpler dynamic programming challenge that introduces the concept of skipping elements to meet constraints. Practicing these problems can deepen your understanding of the techniques required to solve the dice roll simulation and similar tasks. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is recursive backtracking with memoization. This approach is intuitive and often easier to implement since it mirrors the problem's natural structure. However, it can be less efficient than bottom-up dynamic programming because it may involve repeated calls for overlapping subproblems. The recursion stack also makes it more memory-intensive. Bottom-up dynamic programming, on the other hand, is the most efficient approach. By avoiding recursion and computing results iteratively, you can maintain a compact DP table and achieve better performance. That said, it requires a solid understanding of state transitions and careful initialization. Lastly, you can optimize space by using a rolling array technique, where only the last few states are stored instead of maintaining a full DP table. This significantly reduces memory usage for large-scale problems, though it can be slightly harder to implement. Choosing the right approach depends on your comfort level and the constraints of the problem you're solving. Great job! We've covered the dynamic programming approach to solve the dice roll simulation problem. Remember, mastering problems like these helps you identify patterns and refine your coding skills. Thank you for watching, and I encourage you to practice more problems like this to further solidify your understanding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!